Okay, so we are going to talk about chapter 17D. Arrhenius equation. So Arrhenius equation is the reaction rate is A to the exponential minus RT over activation energy. So this is an Arrhenius equation to show that how reaction rate constant R as a function of temperature. So this is empirical, and this is the person, the Arrhenius, was put it up. So this one is essentially temperature dependence of the rate constant, and the way that this one was worked out is natural log of rate constant versus 1 over temperature should be a linear relationship, and this is an inspiration that he got from Bantoff plot, which is ln equilibrium constant K is a function of temperature. How the equilibrium constant depends on temperature, how reaction rate depends on constant temperature. So he's kind of borrowed this idea too. Okay? And there's a lot of similarity in between these two. So if you look at that, Arrhenius plot is 1 over temperature versus natural log of reaction rate. And this one should have this linear relationship. Over temperature, this is a recap of what we've done before. This is a Bantoff plot. Okay. And this is Arrhenius. And so they are quite similar, and the slope here is minus R to the EA, and slope here is minus R to the delta H, essentially, but this is for the reaction and the standard condition. So this one, EA, has what we call the activation energy. So who won the first Nobel Prize in chemistry? Yeah, he's the first Nobel Prize. Okay. Chemistry. He's a second. No. He's a third chemistry Nobel Prize. Do you know who got somewhere in between? Who is the second Nobel Prize winner? Did anyone bother to look at that? You guys, do you remember organic chemistry? You guys heard about Fischer projection? Yeah, he's the one. Okay. He didn't get Nobel Prize for the Fischer projection, but he understands the, I guess, organic chemistry portion of it. Okay. So let's talk about what this A and B means. So once again, the equation is KR is A e to the minus EA to the RT. And A is what we call the main term is a pre-exponential factor. It didn't say anything, right? It is a factor that goes in front of the exponential. Okay? That's a pre-exponential factor. And it is used that way too. And other term that people also using it for is called a frequency factor. So it has not much of the it has a concept about when things to react, they have to have a collision, and certain frequency of the collision is related to or the rate of reaction. So the higher the A value is, the higher the KR. But it is not much of the big emphasis on understanding the A. But what's most important one is the EA, that's what we call the activation energy. So it has a unit of energy, and if you look at that, EA divided by RT. Do you know what's the unit of RT? Anyone remember? Energy? That's right. Yeah. Therefore, the top one should be also energy. You know, energy is an extensive quantity, so you have to normalize by the per mole basis, and then that's what's a unit. And with, it's always shown up this kind of reaction coordinate. So when you have a reactant and the product, and then this is, let's say, the energy level. Let's say you have this kind of diagram. This one shows that this is in the reactant, this is a product, and the energy state before and this is an after, energy states are dropped in this way. So this amount of energy is actually liberated to the surrounding. So that's why we call exothermic reaction, right? Okay, so this one I can just set, and then this is probably related to delta H R on that, and then in this case this is a negative, so it is decreasing. Okay, if the magnitude of this one is big, if actually your key value is big, so they favor much product more. So this difference is actually related to the big K. So the bigger the drop you will have, they will favor the product more and more because higher delta H magnitude, higher delta G magnitude. The delta G, you remember that, right? Delta G reaction is minus RT ln K. So they are related. So the bigger H, bigger G, bigger K. Right? So you can all relate it that. So this difference between that and that is about equilibrium chemistry. Right? So now we are talking about this factor. This is what is important in kinetics, and this is what we call activation energy. And you have to overcome this barrier to go to the other state that is simple. And I remember, some kind of the textbook before, this is a thing that you can see that. This is a state A, okay? And this is a state B. You see that, right? So this is, sometimes people call it, this is a reactant. I know that this state it has a lower energy. But if I let it go, does it go to lower energy right away? No, you need to have certain energy barriers, right? So even any process or any transition changes require some sort of an activation. And it is your activation energy is normalized by RT. RT is essentially thermal random fluctuation energy. So this energy is essentially normalized by this, and that is how the Arrhenius plot is worked out. And if you put a catalyst, somehow if they do this, right? If they do that, they can lower the activation energy. This changing is a lot more faster, so that you can acquire your product not in days, but in minutes. And then your reactor site doesn't have to be big, it can be very small. And that's why that's where all the monies are, okay? So this is why there's a big portion of the chemists working on designing different kinds of the chemical for the activation, to reduce the activation energy. That's what we call the catalyst.